Let's talk about curly arrows, making and breaking single bonds. We're going to approach this from the very basic, and I'm going to talk about the physics of it. Okay, if we just have a nucleus with one positive charge in it, what do we call that?
A proton.
If I bring an electron close to this proton, is it attracted to it?
Yes.
Where is it going to go? To answer that question, you have to understand that we can't really be sure where the electron is at any instant. What is Heisenberg famous for?
Heisenberg uncertainty.
Principle, yeah. Who calculated wave equation?
Schrödinger.
Yeah. Heisenberg didn't know, but Schrödinger said, well, I can calculate that. And he came up with his wave equation. He predicted that the square of the wave equation would describe a probability surface or an orbital. An orbital is like an empty bookshelf. In atoms, where do you fill the bookshelves? Do you start at the lowest energy first or the highest?
The highest.
Are you sure?
The lowest energy.
The lowest.
Always.
Yeah, always the
prefer
lowest.
lower energy.
And that's got a name, actually. I don't suppose you remember it. Sophomore principle, I think. Okay, we pop in the electron in the lowest energy bookshelf, lowest energy orbital, which happens to be this s orbital, a spherical surface. The probability of finding the electron on that sphere will be maximal, according to Schrödinger. As I bring two protons together, would it possibly be beneficial to recalculate the wave equation to maximize the interaction between them?
Yes.
What happens to the shape of the probability surface then?
It will change.
It will change. The shape of the molecular orbital, which represents that first bookshelf, changes too. If I don't have any electrons there, will the protons approach each other in the first place?
No, because it's a repulsive force.
Yeah, they hate each other. But if I kind of insulate one proton from the other with an electron, is that better?
A bit better.
It is, yeah, because at least there's one negative charge to sometimes be between the two positives. If I put two electrons in that orbital, would that be best?
It would be best.
Yes, and then we get something neutral. The two positive charges of the nuclei are balanced by the two electrons. Okay, that's the physics of it. Let's look at the chemistry. What do we call one positive charge on its own? We call it a proton or a hydrogen cation. If we add an electron to that, pop it in that orbital, what do we get, Yuan?
We'll get a hydrogen radical.
Hydrogen radical or hydrogen atom. Yes, good. Hydrogen atoms, are they reactive?
Yes, they are.
Yeah, they're reactive because we don't have a complement of two electrons in that orbital, and it will hold two. Okay, if we take our hydrogen atom and we add another electron to it, first of all, what's going to be the charge of the product?
Negative charge.
Negative, because we have one proton, two electrons. Okay, let's drop it in the orbital. And we get a hydride anion. You shouldn't call a proton a hydrogen atom, and you shouldn't call a hydrogen atom a hydride anion. Let's go back to the hydrogen radical. One happy day, it meets another hydrogen atom. So what is this arrow here?
The half arrows mean the electron is being moved from the hydrogen to that empty space.
Yes, good. The position of the start and the end of the arrow are very particular. The fact that it is a fishhook, we call it, means only one electron is moving. I can draw two of those fishhook arrows to come meet each other. The point at which they meet will be the center of the bond between the two hydrogen atoms, and that is called a
Sigma bond.
sigma bond. Good. Sigma bonds, by definition, are head-to-head interactions of orbitals. So let's go back to this theme of two hydrogen atoms interacting with each other, and now they've got two electrons in them, so it's a stable arrangement, and the molecule is H2. Let's consider what happens when we take a hydride and we react it with a proton. Are we going to draw an arrow from the proton to the hydride?
No, because the proton doesn't have any electrons.
Yeah, so which way do we draw it, Yuan?
We are going to start from the hydride since it has 2 electrons.
Good. Will we use a fishhook?
No, because there's 2 electrons.
2 electrons. 2 electrons gets us a whole arrow, not just a little piece. So we draw it like this, where the end of the arrow means that's where the electrons go. You always put your pen or your pencil on the electrons and you push. You don't sort of suck them. Does it matter if I draw the arrow very tall?
It wouldn't matter unless you want to waste space on your paper.
Okay, yeah, that's a very green thought there. Would it matter if I drew it very short then?
No.
Yes, it would. It'd save you paper.
Yeah, indeed.
How about upside down?
No.
Upside down is fine too. It's all legitimate. Curvy?
It is perfectly fine.
Perfectly fine. It's only really the beginning of the arrow and the end, the arrow head, that makes any difference. What's wrong with this arrow to describe a hydride reacting with a proton?
There's supposed to be 2 electrons, but the arrow is only a fishhook.
That's wrong. You see, the lone pair isn't shown here, but you don't have to in organic chemistry. What's wrong with that arrow, Yuan?
That arrow is pointing from a proton, which doesn't have any electrons.
It doesn't have any electrons, you can't push from it. What about this arrow?
This arrow is starting from an empty space to a hydride. There's no electron from that empty space, so there's nothing to move.
Good. And could the hydride comfortably accommodate another electron?
No, it's full.
That is a disaster. What about this arrow?
This arrow is from an empty space to another empty space.
Exactly. That one is a calamity as well. Students who don't understand arrows draw anything, hoping that the grader will be merciful. And they're not. They see through these arrows pretty quickly. Thank you to everybody who's listening.
Ma salama! Problems like this can be found in the workbook Sophomore Organic Chemistry by Inquisition, Volumes 1 and 2. These are available for $35 each from www.byinquisition.org, and the answers to both sets of problems are available on that website too as downloadable PDFs.